Welcome back to ArmanisMath. Today we're going to focus on Chapter 3, the Exponential and Logarithmic Function. Exponential and Logarithmic Functions. So, right objective, we'll be able to identify exponential function and their graphs. I'm going to start with a very simple approach that is called a squaring function or quadratic function. This is going to be a review and at the same time a warm-up. F of x is equals to x squared. We know this is the parent function since there's no transformation happen. There is no transformation happening here. So I have a vertex at 0, 0. And I'm looking up a happy face. Okay. We also looked at it being transformed, f of x, and by this you should by now you should know the transformation. So let's say x minus 3 to the second power plus 1. Can somebody tell me the h and the k for this function? H and k. H and k. H and k, a lot of you have given me h and k as if it's vertex, which is fine. I'm okay. So h and k is here. H, horizontal. Yes, thank you. You are moving to the right 3 units. And how about the k? Is it up or down here? K follows the same sign that you see here. So now I know that I'm shifting this dude here to the right is 1 and 2 and 3 and up 1. So basically I'm gonna look like that, okay? With this vertex as 3, 1. Okay, why did I go through this? Well, because we want to kind of follow the same pattern, if you might, with the exponential function. Okay, so first thing first, in exponential function, the variable is actually the exponent. So for example, this is f of x equals 2 to the x power. That's not the same as this one, by the way. This is x being the base, 2 being the exponent, and 2 doesn't change here, right? It's always 2. Here in exponential, it's a little bit different. This is exponential. Obviously, this is quadratic, right? Okay, so 2 is the base, basically the constant in the base. And the biggie thing about exponential is the variable here. This is the exponent. And the exponent is actually a variable. That exponent changes. The base stays the same. So this is base. Base is always at the bottom, by the way. Base is the bottom. Base is down there. So here's the base. Base doesn't change. Okay, and to graph this, that's the y-intercept. And on the right side here, I'm going to put, you guys can help me with this one, okay? I'm going to put a table here and put some values, okay? I'm going to put some values for this. So this is x, 0. So 2 to the 0. If I put 0 for x, what would I get here? Yep, anything to the 0 is 1, except itself, right? What if I put 1 for x? What would I get? I see a lot of chats coming up. Good, good. And what if I put, let's say, 5? 5 for x. 5, Armani will give you 2 to the 5th, which is 32. And you could tell right off the bat, I mean, numbers are going to increase very rapidly. Numbers are going to shoot up very quickly. What if I put something negative? So let's say, for example, what if I put negative 2? So now, pay attention to this one here. I've got 2 raised to the negative 2. Uh-oh. I have a problem here. Because I know from the first 2 weeks of this class that exponents do not like to be negatives. They just don't. So we did something earlier in the year, which by the way, there's some videos on that, exponents. flip the base. If this exponent's negative, you make it positive by flipping the base. If the base is 2 here, that becomes 1/2 to the second degree. And now the exponent is happy. So now let me try to graph this. So if I put -2, I'm going to kind of exaggerate a little bit here. So I'm going to say this is -2 here. -2 takes you to 1/4. And let me also exaggerate a little bit and put the 1 here. This is 1 here. So 1/4, maybe I'm somewhere here. Here's 1/4 for me. And if I put -1, it's going to give me to 1/2. So probably somewhere here. If I put somewhere here. If I put 1, it's going to be like this. It's a curve, by the way. So it's probably down here. And then if I put 1, it's going to give you 2, etc., etc., etc. So and you're going to see yourself shooting very fast. Ooh. You wish like this is like your bank account or something. Okay. The main point here, I'm going to put that in red. Main point here for us is 0, 1. Okay, keep track of this point. That's going to help us a lot. We call this as an exponential growth, and you could tell the value is growing here, right? You are starting from 1/4 to 1/2. Obviously, you're growing. From 1/2 to 1, you're growing. From 1 to 2 to 32, etc., etc., etc. Okay. I actually could put some more points here as well. Let's put 2. Let's see what would happen if I put 2, by the way. What would happen if I put 2 here? Function. So this ratio here, this common ratio here, right, is going to be your base for the function. So basically you have a base of 2 raised to the x power. Just based on this table here, the ratio is 2 and it's raised to the x power because this is an exponential function. So from a graph you're able to deduce the function itself. What's the base? So maybe I could put a different color here. So this 2 here, this 2 here, this 2 here is the base for your function. Okay, and you graph it, and as we said, this exponential growth, it goes up like that. So also, we just talked about the quadratic formula being not an exponential because the base is actually x. Yes, the rate of change is actually times 2. You're right, times 2. The quadratic function is not an exponential because it's got the x at the bottom, not at the exponent, versus the other one as that. So to generalize this, the exponential function would have this type of equation here. F of x equals a. A is a factor, by the way, just like the a that we have in other functions that helps you stretch and shrink vertically. B is the base raised to the x power. So in this case, again, a is going to be the determining factor that we're going to talk about in terms of shrinking and stretching. So let's take a look here. What is and what is not an exponential function? First of all, 3 to the x is an exponential because I have an x as an exponent. Keep that in mind. X as an exponent is the key to exponential function. How about this one here? 6x to the -4. Is this exponential? The answer is no. To be exponential, Armani, you have to have x as an exponent. This is not the case here. You have -4 as an exponent. So this is not an exponential. The first one is. How about this dude here? I've got -2 times 1.5 raised to the x power. Is this exponential? -2 times that. It is an exponential, yes. An exponential with an x at that exponent. And what's the a term here? Does anybody give me the a term? Exactly. A equals -2 here. So apparently there's something going on in terms of flipping and something which we're going to talk about momentarily, okay? But I know the base is 1.5. And by the way, if the base is a number that is more than 1, you are growing. is between 0, obviously greater than 0, and 1, you have an exponential decay. Let me put that at the top here. Decay. If the a is greater than 1, the base, I'm sorry, if the base is greater than 1, you have an exponential growth. You're growing. And the graph for this, for each one of them, is very simple. You kind of intuitive, but let's just graph it here for you. Growth would be something like this, starting very, very, very slow, and then all of a sudden shoots up very fast. We looked at that 0, 1. I'm touching the y-axis here. That's y-intercept at 0, 1. Same thing with growth. It's going to start very fast and then slows down closer to 0. That's decaying. You're decaying. The 0, 1. Okay, we call this decay, and we call this growth. Depends on the base. Okay. This one here, it says an exponential function with the 7 as a base, and a base of okay, hold on, let's 7. I'm gonna put this here, 7 times 2 to the negative x. I'm getting a negative exponent. Alert, alert, what do I need to do? Negative exponent, what do I need to do? Who's unhappy here? Who's unhappy? Flip the base. Yep, that's not right. We do not like this kind of stuff. So you had to put 7. Leave that alone. That's not your base. 7 is not your base. That's the a, okay? Your b is the base, which in the case is the 2. It becomes 1/2 as the base, raised to the x power. So can you tell me if this 1/2 is the base, is this growth or decay? That's it. It is a decay. That's very true. All right, let's talk about this one here. And we almost touched on every single one of them, but let's just again touch base again. The function that you have is 2 to the x, and they're giving you some values to like basically table values. If you put 4, it's going to give you 16. If you put 0, it's going to give you 1. If you put -3, well, you're going to have to flip, right? -3, this becomes 2 to the x power. And if you said this is 2 to the -3, let me choose a different color for that. 2 to the -3, well, again, that's not going to be happy. It's 1/2 to the 3rd, which is 1/8. Okay. Now let's move on to basically exponents that has fractions in them. And I'm going to start with a very simple one here, not like the one in textbook. So I'm going to start with a simple one. Let's say I have a 4 raised to 1/2. 4 raised to 1/2 here could be rewritten as square root of 4. And remember, the bottom of this fraction here is the actual index to the root. So this is 1/2, this is the second root. 4 to the 1/3. What kind of root do you think I'm going to have here? Exactly, it's a cubic root. This is a cubic root. And I have 2/3. Aha! What are you going to do? So I'm going to put some work on the side here. I like to do my work on the side. So what I'm going to do here is think about this fraction here. Okay, I'm going to dissect this fraction a little bit. 2 to the 2 over 3 is the same as 1/3 times 2. Do you agree? 2/3 is 1/3 times 2. Yep, stay with me. Yes? Is this true? So I know that I could split this guy into 2 things. This is actually 8 to the 1/3. The whole thing is raised to the second power. Well, I know by now the 1/3 power is going to be the cubic root. So that's a cubic root of 8. Raised to the 2nd power. So here is my 2nd power. What's the cubic root of 8? I know the value for this one. That's a 2. 2 raised to the 2nd power, which is 4. Okay? You want to do example like this, or are you good to go? You need one more example like this? Let me know. Looks like we're good. Awesome. So now let's talk about negatives. Let's say, for example, I have a 27 negative. I'm going to say 2/3 as well. Okay. Which is 2.5 times 1/3. 2 is the cubic root of 8. Okay. Negative 2/3. Negative 2/3. Well, somebody's not happy, right? Right at the get-go, somebody's not really happy here. That's not right. See, we have to make things right here. So what would that be? What do you think I'm going to flip? Walk me through it. What do you think I'm going to, exactly? It's going to be 1/27. And then basically I have this is raised to the 2/3. Now somebody's happy here. Now I have to dissect this one a little bit. Well, this is a cubic root, right? It's a cubic root. A root. I have a cubic root. By the way, you could also distribute the cubic root. So this is basically a cubic root of 1, cubic root of 27, cubic, right? The whole thing is raised to the 2nd power. So we just don't do the 1 because it's just the same number. So 1 is divided by cubic root of 27 is 3. And remember that you still have the 2 waiting for you outside, which is, again, you distribute the 2. This 2 belongs to everyone here, which will give you a 1/9. Okay? Logistic, we're not going to focus on logistic, or just exponential function. And in the objective, it's basically here at the top left, constant percentage rate and rational function. Okay, there's also a growth and decay. We're not going to talk about models. We're just going to talk about it being applied mathematics. Okay, so constant rate of change. This is the R, and that's a percentage. Like how much percentage of populations is, for example, increasing. Let's say that Arizona's population is increasing, Detroit's population is decreasing. Decreasing by how much? Maybe 2% every year, or whatever the amount is. So there's not too much to test in this section, except me giving you values to put in the calculator. I know, doesn't sound really exciting, but the formula basically for this section is found here. This is a formula. Basically, they're saying P sub t, t by the way is the time, equals P sub 0. This is the initial value, initial population, and if initial age, if you're using like C14 to measure the age of a fossil, for example, times 1 plus R, rate of change. That's the percentage, whatever the increasing or decreasing by, and then raised to the t power. Some calculators have this actually built in. It's just built in to, the formula is built in. If you don't have it, that's okay. You just make sure that you multiply it and make sure you be consistent. There's nothing really here, nothing really to test here other than me giving you values and you plug them in into the calculator. And that's why we don't spend that much time on this section anyway. So, for example, let's take an example here. It says obviously if R is greater than 1, just like the base, remember this looks like exponential, right? Because there's a variable at the top. I'm going to put this one more time, very big, very loud, very clear. This t is a variable, just like the x, the y. So if t is the variable at the top as an exponent, this is automatically an exponential, right? Exponential. The base, though, has to be 1 plus the r that change. So in this case, for example, it says if the r is greater than 0, like positive, 1, 2, there's a growth. I'm going to expect to see growth in the population, for example. If r is less than 0, and this whole value is less than 0, whatever makes the base for my exponent, whatever makes the base here less than 0, well, obviously it's going to be decay, right? We looked at that in last section. Let's say I have a 1/2 raised to the x power. Well, obviously this is the decay, right? What if I have 2 to the x? That's growth. Growth, decay. Same thing here. So basically, all what you have to do is actually 1 times that. 1 plus the base, the rate of change in this case. So here's an example here. This one says, find the growth and decay. Tell whether the population model is an exponential growth or decay for these two cities. So San Jose, P of t, that's a function. It's given you this humongous number times 1.0064. What? 1.0064 to the tth power. Is this exponential? First of all, is this exponential? Yes or no, guys? Yes, it is. Is this exponential growth? It depends on the base. Is the base more than 1? Yeah, Armani, kinda, sorta. Yes, it is. Even though it's like really tiny bit more than 1, but still it's more than 1. It is still more than 1. 0.0064. That's more than the 1, right? That's 1.064 is more than 1. So obviously, the base, that's going to be an exponential growth. Basically, what they're saying here is San Jose is going to grow in its population. How about Detroit? Well, Detroit, let's take a look here. What's that number here? What's 0.98, whatever the thing is, right? Well, that's not growing, Armani. Why is not growing? Because you're less than 1. So exponential decay for Detroit is what we expect. Okay, that's a population growth. You also could use this again for bacteria growth, for some other applications. For example, you determine the exponential function with the initial and increasing with the initial value of 12 and increasing at rate of change was 8%. Again, I'm going to put this in my function, P of t. I'm going to also indicate a couple things now as we talk about this. P of t, time, by the way, is always in years. Time is in years. Okay. If you want to put months, then you have to do, you just adjust that. I'll show you what to do in a moment. So the initial value is 12, and then this is 1 plus. They gave me the rate of change, which is 8%. How do you write 8% in decimal? How do you write 8% in decimal? Exactly, 0.08. How do you write 6% in decimal? 0.06. Good job. Okay, so that's 0.08, 0.08, 08. Well, right off the bat, do you think this is going to increase or decrease? You think we're going to grow, or are we going to, is this going to be growth or decay? No, hold on a second. Remember, it's both. You have to add 1. In this formula, you got to add this base. This is the whole base. Be careful with that. Exponential growth and decay formulas, there's a 1 there. So, yes, exactly. You have to grow. Even if it's a little bit of money. I know, but still greater than 1. So, it is more than 1, so you have to grow. Basically, you're going to grow by amount. Now, the time is what I wanted to talk about a little bit here. T here for time, T for time, and T is always in years, okay? T is in years. Okay, what if you want to put your money into a savings account and they told you, you know what? We have this awesome deal for you. we could compound your money every single month of the year. What does compound money means? Well, if you put $1,000, for example, every single month we're going to give you, I'm being obviously silly here, we're going to give you 5%. Every single month, 5%. What? Yeah. So here comes January. You're going to take the end of January, you're going to take the 1,000 that you put, plus how much? 5%. What is 5% of 1,000? 5% of 1,000. 50. Exactly. So at the end of January, you're going to have $1,050. And then they're going to take the $1,050, so one like this, and they're going to take you, they're actually going to give you 5% on top of that. What does that mean? Well, I know 5% of 1,050. What's 5% of 50? Ha. What's 10% of 50? 10% of 50, exactly, 2.5. So you're actually going to get plus 2.5. 1,005, actually it's going to be 52.5, right? 52.5. So at the end of February, you have 1,052.5. And obviously, I mean, that's being hypothetical here, but if that's the case, I would definitely put some money there because that's a good deal. That this should be, well, I guess my whole point for this is the rate of change instead of years, instead of them saying, Joseph asked me towards the end, okay? Instead of them saying that this is a year, like once a year, you get 5%, they're actually telling you every month you get 5%. So you're going to change this year's into 12 times instead of one time for a year. I'm done with this, okay? Very last one here. It says, I'm going to have to get going here. One, this is a 2, and we do have time. Good. Okay, anyways, one more example here, and then we'll have to jump to the most important section, which is 3.3 for us today. This one says modeling bacteria. Suppose the culture of 100 bacteria is put into petri dish, and then culture doubles every hour. Okay, so in the dish, culture doubles every hour you're gonna get twice as much. So it's 200, 2 times 100, 4 times, because you're doubling the 200, the 800, etc., etc. And if you looked at this carefully, you're gonna find out you actually have a base of 2 raised to a power, and times 100. The a is 100 in this case, which you probably could tell by now. That's gonna be a humongous growth here, right? Very much growing, vast. Oh, Lord, help us with this pandemic. It does grow fast. I'm not sure what kind of modeling they have for this pandemic, but probably it's close to exponential. I have to dig that out, or maybe you could also look that up, what kind of modeling they used for statistics. For example, they predict such and such number of cases we're going to have of COVID in the next month or so. They use models like this. Could be exponential. I'm not too sure what kind of model, but definitely using mathematical modeling for that. All right, champions. So as I said, there's nothing really to talk about in this section except that little formula here, which I will definitely have to give you numbers to plug it in. Okay, moving on. It could be hours. That means you really have to multiply by a lot of things to get that, Leila. If it's hourly, that means you have to multiply by the year, month, change that to, that's a lot of time. Or two for time, yeah. If they ask for hours, or if they ask for minutes or seconds, there's a lot of multiplication happening here. If this is the case, yes. Okay, guys, let's talk about this one here. 3-3 is the logarithmic functions and their graphs. So the objective is at the top here, objectives. It says I will be able to recognize the inverse of the exponential functions. Also use a common logarithm base of 10. And most likely I'm not going to get to the last part today. But definitely the first two of the objective. They want to start you off by looking at the logarithmic function. They said, you know what? We're not going to start you with logarithmic function graphing. We're going to start you actually with the exponential function. So we did just finish exponential graphing right now, like a few minutes ago, right? Exponential growth looking like this. Exponential decay looks like that. Does anybody recall what this point is? What was this point here? What was the main point, the y-intercept for the exponential growth and decay, for the parent function? 0, 1. 0, 1 for both. You intersect the y-axis at 1 on both sides. The parents, right? So now they also are telling us that this is kind of related to the logarithmic function. What does that mean? What does that relating means? Well, logarithm and exponentials are inverses of each other. Logarithmic function, and exponential are inverses of one another. So if exponential looks like this, which is, let's say this green line that I have, if this is exponential, the inverse of it is actually going to be log, which is the black one here, the inverse. We're talking about this graphically here. Does anybody recall the 4 steps of finding the inverse of a function? The 4 steps to finding the inverse of a function. Could you give me any of these 4 steps? I guess this is called spiral review, so I review as I'm teaching. There's more than this amount of people. I need to participate. See participation. Here we go. Multiple users are typing. Here we go. Participate, participate, and participate from now until the end of the semester. Trust me, it's going to only help you. It's only going to help. I see some said replace switching y x's with y. That's true, and then you solve for a y, and then you change that y to this f of x. That is very true. That was algebraically. That's what you do, by the way, right? So how do you find the inverse graphically? That's what they're talking about here. You find the inverse graphically by using the y equals x line. You reflect over the y equals x line, which is, by the way, the 45-degree angle line. Don't tell anybody I said that. What was that? What did you just say? What did you just call him? Okay. The 45-degree line. Okay. Oh gosh. Okay. So if you reflect over the y equals x, or the 45-degree line, you've reflected your exponential. Exponential. If you reflected your exponential over the y equals x, you're going to find yourself looking at the logarithmic function. Logarithmic. That's the black one here. Okay. You do recall that we have an asymptote for the exponential. Does anybody remember what was the asymptote? We graphed it. We talked about it. Yes, the x-axis, and we call this y equals what? Does anybody remember that? Y equals something. Y equals 0, that's right. So y equals 0 was the, let me go back to it again. Y equals 0 was the, let me use similar color for that one. Y equals 0 was my asymptote, horizontal asymptote, right? Well, they're telling you also that there is a vertical asymptote for the logarithmic. Vertical asymptote. So there is another one here. I'm going to actually choose, I've never used the black for this, but I'm going to use it. as an S. See, there is for the black one, which is a logarithm, there is a vertical asymptote. I can't cross that. Basically, this tells you there is no log of a negative number. Look at that. There's no log of a negative number. Can't have that. Come so close to 0. So close. Can't touch. We can't go beyond that. That's my little kid here. That's nice. I love my children. I'm sure your parents do. Okay. How do you go from the logarithmic to the exponential? I'm going to spend time here. Okay, so make sure you take notes, okay? How do you go from logarithmic to exponential? I'm going to go here and put log to exponential. How do I go from one to the other? Log from logarithmic to exponential function. Okay, let's look exponential here. Logarithm. So I'm going to start with an easy one here. Okay. Are you going to cover conics? Next semester, yes. Leila, next semester. Exponential. So let me actually start with a very simple example here that we actually looked at earlier. 2 to the third equals how much? Does anybody give me the value? What's 2 to the third? Leila, I think you're still referring to conics, and the answer is yes. To the 8, okay? 2 to the third, it gives you 8. I wanted you to follow along with me here, okay? So I'm going to label things. Make sure that you do that same, please. This was the base. Okay? This was my exponent here, obviously. This was the answer. Okay? Now, to move from exponential to log, have to follow the same thing. Base is always at the basement, so I'm going to say log base 2. Base is always at the basement. It's at the bottom here. And I'm going to loop counterclockwise. I'm going to put equal sign here. I'm going to say log base 2 of 2 to the third power gives me 8. And this is the way you do it. I'm going to give you the loop here. 2 raised to the third gives you the answer. If you have questions, you really like the answers, right? If you usually in life, if you have questions, you really like the answers. Is that true? Yeah? So same thing with log. Log really likes the answer. So the answer is always next to the log. The log always hugs the answer. Are you with me? So you don't confuse where you're going to put the 3 and the 8. Log always hugs the answer. So the answer is going to be here. And you do this counterclockwise, this loop here. 2 is the base. Don't forget, 2 is the base. That didn't change. 3 is exponent. Gives you the answer, which is right next to the log, because log hugs the answer. Log hugs the answer. Did you get that? Give me a yes if you're doing good. Okay, now actually we're gonna practice this, right? So we're gonna do some more. What if I want to go the other direction? What if I want to say, for example, log base 3, 27 of 3. How do I move on to the exponential form? Somebody help me out. What's the base? Base is 3. What's the exponent? Third equals the answer, 27. And I did this just by following my loop. 3 raised to the third. 3 raised to the 3, I should say, gives you 27. Gives me the answer. 3 raised to this third degree gives me the answer, which is 27. Okay. Later I have to wait for that a little bit. So for this here, let me actually start you with, give you a different example. What if I said, give me something like this? This is a little bit tricky, okay? But stay focused, okay? The things do not change. Just a little bit tricky, but it doesn't change. Just a little bit spices here. A little bit spices. Does anybody like spicy food here? So I love spices. Jared. Abby. Kayla. I like spicy food. So let's say I have 5, and this one I'm gonna go berserk. I'm gonna go like actual 25, I should say, raised to 1/2. 25 raised to 1/2. What? How much would that be? Yeah, that's a square root of 5. Oh, goodness. 25 raised to 1/2 is actually going to be 5. Well, how do I write this here in terms of logarithmic function? Log, what's the base? 25. Base doesn't change. Log of 25 of what? Where am I raising the 25 to? What's the power? What's the exponent? 1/2. That should give me the answer, which is very dear to the log. The log hugs the answer. It's really very dear to it. So that's going to be the one that you look at that. Okay? Let's take a look at the examples that they provided, and hopefully we'll take a look at that. So log base of 2 of 8 is equal to 3. It's 2 to the 3rd equals 8. Log 3 of square root of 8. I'd like to do number letter B here. Let's do that. So what if I said I have a log base 3 of square root of 3 equals 1/2. How do you write this one in terms of exponential? Exponential. What's the base? 3 is the base. Raised to what power? Here we go. Gives me the square root of 3. That's what we do here. Simple as that. Okay, how about this dude here? This one says I have log base 5 of 1 over 25. What? Well, basically, raise 5 to what power gives you 1 over 25? 5 is the base. Raised to what power gives you 1 over 25? Well, basically, it's going to be -2. You're going to have to raise it to -2. And that's why it goes to the exponential form like that. Let me put it down just for those who might need it. Log base 5 of 1 over 25. I'll put the base all the way at the bottom here. I have a 5 down here. Equals -2. So basically, if I want to move exponentially from there, or transfer it to exponential, I have a 5 raised to the -2, which definitely is 1 over 25. Okay. They also wanted us to know a couple other things. For example, when you raise something to the 0 power, does anybody know how much is that? If I said, for example, 4 to the 0, that's going to equal to 1. How do you write this in log format? How do you log this in log? What's the base? Log base what? Base 4. Base 4, and then you raise the 4 to what power? 0 will give you the answer, which is 1 over here. Okay? Just follow the loop. You should be fine. Another one that you want to also mention to you here is, let's say I have a log 5 of 5. Well, what takes you from 5 to 5? So it's 5 to what power gives you 5? To the first power. So basically, I have to have an equal 1 here, right? So if you see a log of a base raised to the same number, log of the base of a number raised of the same number, like log 5 of 5, log 6 of 6, log 7 of 7, you know the value of it is just a 1, because you know you could just put the exponent as 1. Okay, let's see some more. We talked about that. Some properties of, basic properties of logarithm. To the 0, we said it's 1, right? And b of b, we said this is 1. This is another interesting one here, and I probably would just give you a heads up on it. This looks like something we call the power rule for log. So this one says, for example, log, I have, let's say, 2 to the 4th, but that thing is actually moved on to raised to the 3rd power. Okay? So what they're saying here is, hold on a second, log. Okay, hold on a second, because it looks like I'm giving you 2 steps in one. I'm going to go to 2 and then 3rd, okay? To the 3rd power. So can somebody tell me, we just talked about this, by the way. What do you think is log base 2 of 2? Does anybody recall we just talked about this item here? Here we go, 1. And 1 times 3, so basically you have 1. This value is 1. Times 3 is going to be that 3. Okay, there is another example that we have down here. Let me give you that example here. And that's going to be this one here, letter B. Okay, here we go. If I say log of base 3 of square root of 3. Well, this is same as log base 3 of 3 raised to what power? How else can you write the square root? How else can you write the square root in terms of a power, an exponent? What's the square root in terms of exponent? Like square root. You're getting close, Selma. Square root is 1/2. That's right. So now I know this value here. I know this. Dude, this whole thing is going to be 1. 1 times a half will give you the half. Okay, so I know this is 1, and I've got a half here. 1 times a half. This is times, by the way. That's going to give you a half. Last property for this section, for this particular example, is this one here. Let me scoot up a little bit. Is this one here. This one says a weird property in logs, but it's useful sometime. What if you actually have the base raised to a log of the same base? Base raised to a log. So the exponent is actually a log of the same base of x. Well, there's something in math that something called undo. These two guys undo each other. They dissolve, leaving you only with x. So x is going to be the answer for this item here. Okay. These two, if you have a base raised to a log of the same base, they undo each other, and you're going to end up with just the answer that you started with. So here's an example of this one here, which is letter C. It says I have, let me give you a different example. Let's say I have, for example, I have 7 raised to log base 7 of 11. 711. Okay. If you have a base of 7 raised to a log, let me should be more organized here. Log, just to emphasize the fact that we're talking about this, of 11. This is the base, the 7 raised to a log of the same base. Well, this thing, we said this undo each other here. That's the whole, it's going to go away, leaving you only with 11. So the answer is going to be 11. Okay. A common base of 10. Common base of 10. This one here says log. Okay, let me spell it out carefully. And if you see a log, I might actually start with a very simple one. Let's not talk about logs. If I put x, what do I mean by this one? How many x's do I have here? 1. But I don't see 1. Armani, there is a 1 here. There is 1. It's kind of an invisible 1, right? There's 1x. And if I put square root of, let's say, x, what's the index for this root? What's the index for this root? 2. Armani, I don't see it. Yes, I know, but it's called common. It's common root. You have 2. That's common. Same thing with log. If you see a log by itself with no base, there's always a base at the bottom, which is 10. We call this common base. Okay? If there's no base, there's always 10. Just like here. If there's nothing, there's always 1. Just like this roots. If there's nothing, there's always a 2. Logarithm, if there's nothing, there's always a base of 10. Okay? So let's take an example here. It says, for example, log 1 equals 0. Slow down, Armani. Where is the base? Where's the base here? I need a base for log. What's the base do you think here? What's the base here? If there is no base, what is my base? Exactly, it's 10. If there's no base, there's always a 10. There is a hidden 10 here. There is a hidden 10. And let's see if that actually makes sense. I'm going to verify this, if this is true. Well, 10 raised to what power? Walk me through it. 10 raised to what power? Exactly, to the 0. Does that give you 1? Yeah. 10 raised to the 0 power equals 1. So that works. This property is true. So if there's no base, there's always a 10. Don't forget that. It's always a 10. Okay, what if they said we gave you a log, and then I have a 10 here, equals 1. What? What's the base? What's the base here? 10. Yes, if there's nothing here, there's a 10. So 10 raised to the first power equals 10, which is a true statement. That's true, right? That's a very true statement. And the other one says log. Let's say I have log base 10. And then I have, let's say, the I'm going to put 2, for example, 2. Okay, well, how much would that be? Log base 10 of 2. Well, what's down here? There's a 10 down here, right? So 10 raised to what power gives you 10? I'm going to hold on a second. So I'm going to actually move this 2 to this side. So it becomes 2 log 10. So let's talk about this section by itself. 10 raised to what power gives you 10? Well, that's just 1, right? 10 raised to the first power is 10. So 2 times the 1 that I got from this guy, which is just a 2. Just a 2. Last but not least is this guy here that says a 10 base of log base x of 10, right? Log base 10 of x is going to be just the x itself. This goes back to the same one that we talked about earlier. So I'm going to erase here and talk about that. The last property here. They're going over the properties again, but with the base of 10. So this is a 10 raised to log, no base. No base. What's the base if there's no base? Yes, I know there's a base of 10 here. So I know there's trying to be sneaky. There's a 10 here. 10 raised to log base 10. Do you guys remember that? When this guy just goes away. Remember that? That's going to give you whatever is the answer in terms of log, which is going to be just x. All right, let's see if we could do some examples on this. Evaluating logarithmic and exponential when the base is 10. So let's say I have the first one here, log base 100. How do you evaluate log base 100? Well, let's take a look here. Log base. Okay, let's take a look here. They wanted me to evaluate log of 100. So think about this for a second here. Log 100, I could break this up a little bit. I know that, what's the base here again? What's the base? There's a 10 here hiding somewhere. So if I could make this 100 look like something with the powers of 10, I mean, I'll be fine. So basically, you're asking yourself, 10 raised to what power gives you 100? And it turns out to be that you're raising this to this, what power? Second power. So that's why the value for this log of 100 is going to be just a 2. That's equal to 2. Okay? Log of 100 equals 2. That's why. So you're going to find yourself doing a lot of this conversion between logs and exponential to get your answer. Logs and exponential, exponential to log. Log exponential, exponential to log. Cordell. Yep, log to exponential, exponential to log. Now let's do the second one here. It says I have a log. How far are we here? I've got a few minutes left. Log of fifth root of 10. Well, let me think about this a little bit here. I have a 10 as a base. So I have a 10 as a base. Raised to some power. Yeah. Gives me 10. What is this fifth root in terms of exponents? Fifth root in terms of exponent. Hello, fifth root in terms of exponents. How much is that? 1/5. It's fifth root. Come on, Armani. Fifth root is fifth. 1/5. Well, look closely here. If this guy equal to this guy, the exponent has to be equal. If the bases are equal, the exponent has to be the same. So this has to be 1/5. So the value for this guy equals 1/5. Okay, that's for this dude here. Let's see number letter C, I should say. Log 1 over 1,000. Well, 1,000 is 1 over 10 to the third. And let's do this one quickly. Log 1 over 1,000. Well, this is the same as log of 1 over 10 to the third. Okay, let's keep going with this thought here. This is log 10 to the -3. Do you agree? Yep, we just flipped the base. And then you're going to ask yourself, if you ask yourself in exponential form, 10 raised to what power gives you 10 to the -3? Well, obviously, like you're giving the answer away, it's a -3. That's why the answer for this guy is -3. You'll find yourself again switching from back and forth from exponential to log, log to exponential, just to make things look fine here. Last one is 10 log base 6. So remember, there's a base here, 10 log base 10. It's hidden, right? Of 6. Well, we know that these two guys are going to go away, bye-bye, 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 leaving you with just a 6. All right, champions, this should conclude our lesson today. And this should conclude our lesson today. Be blessed wherever you're at. I'm gonna stick around after for questions. So let me go here.